Right, so in the previous session we have worked on wave packet and time evolution of wave packet. How wave packet shape changes with time. That was simulated. And now in this session we'll go through one-dimensional problems. The first one-dimensional problem is particle in a box. That is the most simplest problem that we come across. Particle in a box. So this is a first model that demonstrates the application of uncertainty, and this is the simplest model that describes the atomic energy levels. How atoms have discrete energy levels is a matter of discussion. Right? Bohr's model em cheptundandi, as long as electron revolves in a stationary orbit, it will not lose any energy. Right? But why? But why stationary orbits are stationary? So that was that explanation was given by de Broglie. So what did he say? Every moving particle is associated with a wave. Every moving particle is associated with a wave, and the wavelength is given by h by m. So particle means what? What are the characteristics of particles? So particle should have finite mass, it should occupy a finite space, so particle should have finite mass and it should occupy finite space, and dynamics are given by the rest of the things. Okay, so it should have finite mass and it should be in motion. All moving particles are associated with a wave. So we can describe its properties using just this equation, that's all. That doesn't mean there is a wave. This is just a mathematical representation, there is no wave at all. Matter waves are just mathematical convenience. Matter waves are not waves. I mean, you can't find it physically, you can't observe it. All you can see is only its effects. So wherever you see like a Davison-Germer experiment, where electron behaves like a wave, all you see is the effects of wave nature can be seen, but there is no wave. Okay, so it is only a mathematical representation that so and so velocity and so and so massive particle will have so and so amount of wavelength. That's all. Okay, so now so what happens? As the mass increases or velocity increases, wavelength reduces. More massive the particle is, shorter is the wavelength. More faster the particle, shorter is the wavelength. Okay, so now I'm considering an electron moving in an orbit. So the electron is also moving, so it is also associated with a wave. So when you link a wave, by any chance, if the wave is a closed wave, means if it has a constructive interference after one complete cycle. You understand that? After completion of one cycle, if the wave superimposes with itself exactly, then we call it as constructor interference, right? So if the radius of the orbit changes, there is a possibility that you won't get constructor interference always. So the condition here is whatever the length of the orbit should be a multiple of wavelength, either 1 lambda or 2 lambda, 3 lambda. I mean, if you fit either 1 wave or 2 waves, 3 waves, some integer multiples of the wavelengths should be fitted into that length. Then what happens? If this condition satisfies, what do you get? 2 pi r is equal to n lambda. So 2 pi r is equal to lambda is what? H by mv. So mvr is equal to nh by 2 pi. What is this? This is the Bohr quantization condition. Stationary orbits are characterized by integer multiples of h bar, angular momentum. The angular momentum of stationary orbit will have integer multiples of h bar. Right? mvr is equal to nh by 2 pi is the Bohr's quantization condition, and we have arrived it from de Broglie's relation. So, as long as the wave superimposes over itself again and again, then constructor interference takes place and energy losses will be zero. That's why they are called as stationary orbits. So now comes the case of particle in a box. So coming to particle in a box. So what is the situation? We're fixing a particle inside a potential where within the box the potential is 0 and outside the box potential is infinity. So there is some potential energy. So by virtue of its state, the particle experiences certain energy, and within the box, let's say if you are considering the box size to be L, from 0 to L, the potential is 0, and outside the box the potential is infinity. So how can you visualize this? అదేమై ఉండొచ్చు అలాంటి ఒక సిస్టమ్. Let's say a simple hydrogen atom, a single electron is trapped by a nucleus. Right? So within the region of that atom or nucleus, the electron is moving freely and it cannot escape out of it. So this is a basic simple model of an atom, simplest model of an atom. I mean, we're not considering any higher order interactions. We're considering a simple interaction, and we're assuming the wall size to be infinity, so that it will never come out of that attractive force. So next better version is finite bulk. So in this, the particle is able to come out of that box. So when it acquires sufficient energy, particle will be able to come out of that box, whereas here it cannot come out. So now we have to see the possible energy levels. So what are the possibilities? So here also the particle is associated with a wave, and you should have constructor interference. Right? So this is the starting point. Let's say this is the starting point. The wave reaches the other end and it comes back. So once it comes back, it should trace the same pattern again. Right? So they are the only possible states allowed. Let's say if you have like this, the opposite wave will come to this point. Again, the wave traces the same path. So these are the only possible wave functions for the particle in a box. Why so? So normal, when you consider a free particle, we're assuming the particle is moving freely within the box. Right? What is the wave function for a free particle? Free particle wave function ఏంటంటే free particle is associated with the wave. So either you'll have a sine wave or a cosine wave or a combination of these two. I mean, e power ikx can be written as right? Once wave function is allowed state, the combination of wave functions is also an allowed state. So if e power ikx is a possible wave function, and if e power minus kx is also a possible wave function, the combination of those two, cos kx, is also a valid wave function for the given system. Okay, so now, so these kind of wave functions, as a particle is free to move, then it will be associated with a wave. It is a progressive wave without any endpoints. The wave associated with a free particle is a progressive wave, right? So now what happens? We're fixing some boundaries. The wave should not enter the region beyond 0 and below 0 and above L. We're fixing some boundaries. So what happens? So when you're fixing boundaries, you're imposing restrictions on the wave. So when you are imposing restrictions, what happens? Only those waves will exist where construct interference is possible. Okay. So for that purpose, you can even have, I mean, you can obtain that from, what are the possibilities? Like the possible Schrodinger equation is what? Dou square psi by dou x square plus h bar square actual equation is dou square psi by dou x square plus k square psi is 0. K is 2 pi by lambda. Otherwise, you can write it as
8 pi square.
H bar square will have 4 pi square. So 8 pi square m. E minus p. So this is the time independent Schrodinger wave equation, and we want to get a solution for this. And general solution is this. These are the general solutions. Either e power ikx, when you substitute e power ikx and take a double derivative, you get k square outside. Right? I mean, you can just substitute and see. If you take double derivative of e power ikx, what do you get? Each time derivative will give you ik. You get minus k square. I square is minus 1 minus k square. So d square psi by dx square is equal to minus k square psi. The same result will appear for even for sin kx or cos kx. So these are all the possible wave functions for the system. Okay. So now what we have to do? We have to apply the boundary conditions. So once you get some possible solutions, you're not sure which one is correct, right? So I'm taking the combination of those two. So psi is equal to a sin kx with b plus kx. So when I'm not sure which one is correct, I'll take all possibilities, a combination of all possibilities, and apply the situations like wave function is 0 at x equal to 0. At x equal to 0, wave function is 0. So what do I get? 0 is equal to a sin k into 0, b cos k into 0. A into 0, b into 1. So the application of first boundary condition gives me b is equal to 0. So it is purely a sine wave, because at the boundaries, at the starting points and at the end points, the wave should become 0. That happens only with sine wave. So the cosine function automatically becomes 0 with this boundary condition. So cosine function will not become 0, so we have to make its quotient 0. So cosine function is still finite, but its quotient becomes 0 for this boundary condition. So this is the boundary condition. What is the other boundary condition? Psi equal to 0 at x equal to L. So already psi is fixed to be a sin kx, b is already 0. So now psi equal to 0 at x equal to 0. A is not 0. So A is finite. So sin KL is equal to 0. Means what? It should be some multiple of pi. Pi or pi by 2. Sin pi by 2 is 1. Sin 90 degrees is 1. 180 degrees is 0. So it should be some multiple of n pi. Either 1 pi, 2 pi, 3 pi. Then what happens? So k is equal to n pi by l. So here the condition is v is equal to 0 and k is equal to 2me by h bar square. So in that case, I mean within the box, we got solution like that. So the wave function is psi is equal to a sin n by x by l. Right. So now comes the question. This is already existing within the system, and we are introducing this number n and pi. Right? So now comes the question, what are the possible values for n? n ఏ వాల్యూ తీసుకోవడానికి అవకాశం ఉంది? All integers. So can we have 0? n 1 2 3 fine, integers. What about n is equal to 0? For n 0, wave function becomes 0. So n0 is invalid. n0 is invalid because the wave function itself becomes 0. Means the system does not exist for n is equal to 0. So that's what, right? Probability. Psi square gives you the probability. Psi itself becomes 0 for n equal to 0. Means what? System does not exist for n equal to 0. So n value starts from 1. Now comes the question, what is the ground state energy? What is the first possible energy? So energy is given by what? From this equation we got energy h bar square k square by 2m, which is the kinetic energy of the particle. Okay, na? So I got that from this equation. E is equal to h bar square k square by 2m, which is the kinetic energy of the system. ఎందుకనండి? Why the particle has only kinetic energy? Because the potential is 0. Within the box, the potential is 0. The particle will have only kinetic energy. Potential energy is already fixed to be 0. We took V equal to 0, then only we got the solution. Right? So all the energy we have is only kinetic energy. H bar square k square by 2m. What is h bar k, by the way? P is h bar k. Okay. So now you can replace the value of k from the equation that we have got. So it is h bar square k square by 2m can be written as h bar square by 2m 2 pi by l whole square. What is k? n pi by l. Okay. Keep it as n. N pi by l whole square. So what is the total equation? It is n square pi square h bar square by 2m square. So that is the kinetic energy or total energy of the system. And n value starts from 1. That's most important. So ground state energy is not 0. So E1 is what? Pi square h bar square by 2ml square. That is the ground state energy of the system. And most usually for classical systems the ground state energy is assumed to be 0. Most possibly. But here in quantum mechanics we got a non-zero ground state energy. Ground state energy is not 0. E0 does not exist. And En is equal to n square E1. So you can plot that and check what are the possible wave functions and possible energy states. And one can obtain this ground state energy even from uncertainty principle. Okay, so what is that uncertainty relation says?
Position moment.
Delta x and delta p is of the order of h bar. Okay, so the uncertainty in position of the particle, let's say your particle within the box, what is the maximum uncertainty in locating it? To be anywhere within the box. So this delta x is equal to L. Okay, so the delta x is L and delta p is h bar. Okay, usually people will take h bar by 2. We'll see that if required. So delta p is h bar by L. What is the kinetic energy? E error, uncertainty error in energy is delta p square by 2. What is that number? Delta p square by 2. H bar square 2ml square. That's all right. Except for a factor of pi.
Position momentum similar to h cross.
So if we take h bar by 2, what do you get? 8 ml square. Is that? So whatever it is, you get that order. The error arised due to uncertainty is the ground state energy of the system. So ground state energy is of the order of uncertainty error, except for numbers. Blue dot. Right? So this multiplication factor is just a number. You can take h bar by 2, whatever may be. So that doesn't make any much difference. So ultimately, ground state energy is not zero because of this uncertainty, because of wave particle duality. Okay. So with that, what are the other observations? So the wave function has fixed boundaries. The wave function strictly becomes zero at the boundaries, right? And so these are the wave functions. We can just plot it and verify. If you take different sets of n values, you'll get different wave functions. And if you take different n values, you'll get different energies as well. So you can just plot it using Octave or MATLAB. So let's say we'll start with let's say I'm fixing the length of the box as 5 units. Length as 5 units. So then my x value runs from 0 to 5 with a step size of 5.1. So now what should I plot? N square pi square h bar square by 2ml square. Energies and wave functions are those. They are the wave functions. Sin n pi x by l. Okay. So if I plot all the wave functions on one graph, I'll get everything plotted here like this. So this is the ground state, this is the first excited state, this is the second excited state. Everything will look little clumsy. So if you add energy to the wave function, so it will be shifted up. So the better option is, let's say I consider E1 to be 1 in my case, but just calculate that once. What is the range of that value? E1, what is this? Pi square h bar square by 2ml square. Let's say take the size of the box to be 1 angstrom. 1 into 10 power minus 10. What is this total energy? Mass, let's say electron, 9.1 into 10 power minus 31. So for an electron bounded in a 1 angstrom size atom, what is the ground state energy? If you calculate that, probably you may get a number around the ground state energy of hydrogen probably. Check it. So you have to consider the energies to be in electron volts. Okay. So pi square is as it is, pi square h bar square 6.023 10 power 23 by 4 pi square. Pi square h bar square 2 m. What is the h value? 10 power 6.626 into 10 power minus 34. 6.626 into 10 power minus 34 joule seconds. Okay, 9.1 into 10 power minus 31 mass, and L square 1 into 10 power minus 10 whole square. So what is that number? Just search in Google, you get some number. 6.626 E minus 34 whole square. E stands for 10 power. 6.626 E minus 34 whole square power operation caret by another bracket 4 into 2 8 into 9.1 into 10 power minus 31 minus 20 10 power minus 51. Here we have 34 square 68. So get that number. Yes, 1 angstrom. And to get the energy in electron volts, you have to write 1.6 into 10 power minus 19. in the denominator. So this number is 37.6922. E1. So what shall we do? We have to plot for each value of n sine n by x by L as well as energies En. So now for n is equal to 1 to 5, let's say, for the first 5 energy levels. What I am trying to plot here is x comma n square E1. So it will plot first energy level, and I want to overwrite x comma n star E1 plus sin n pi x by L. I'm just adding energy. So n square E1 plus sin n pi x by L. Hold on. So గీసిన గ్రాఫ్ మీదే మళ్ళీ సేమ్ క్యాన్వాస్ మీద గ్రాఫ్స్ అన్ని ప్లాట్ అవుతాయి. సో మామూలుగా అయితే వితౌట్ హోల్డ్ ఆల్ ఓన్లీ ద ఫైనల్ ప్లాట్ విల్ రిమైన్, ఆల్ ఎర్లియర్ వర్షన్స్ విల్ బి ఓవర్ రిటన్. సో వెన్ యూ కీప్ హోల్డ్ all the plots will remain intact. Okay, so I'm plotting the energy level, and over the each energy level I'm adding the wave function. Okay, so you have to close it properly. Check that. Keep this even value equal to 1, because all your sine functions are varying between 0 to 1, and that E1 is a bigger number, so you can't see the variations. So just for convenience, keep the value of E1 to be 1. So this is the program. Hold all, L is 5, x is 0.125, E1 is 37.6922, n runs from 1 to 5, x comma n square E1, and then sin n pi x by L. So if I run this, so I get a plot like this, but the problem is sine value runs from -1 to +1, whereas the numbers energy levels we are considering are 200, 400, 600, 800 up to 1000. So you cannot see the variations of sine function here. So for convenience I am setting E1 to be 1 because that's just a number, starting number. So now you get this. So first plot is at 1 unit, next plot is at 4 units, next plot is at 9 units, 16 units, 25 units. So like that the energy level diagram, and this one is the wave functions for different levels of particle in a box. This is the program. So now comes the question. So we have considered so this is the most simplest model for atom, and we got ground state energy as some 37.6 electron volts, right? So now comes the question, how this energy level gap changes when you go to higher and higher energy levels, higher and higher excited states, how that energy gap changes. So in the case of hydrogen atom, the energy is a function of 1 by n square. So as you go to higher and higher energy levels, the energy level gap reduces. Whereas here, energy is proportional to n square. So as you go to higher and higher energy levels, the energy gap increases. So that is the first observation in this case. And when you go to next level, like when you take a group of atoms or group of electrons, that you will come across in solid state physics, Bloch theorem. So when you have a group of atoms, how this energy level diagram changes is a matter of discussion. You will get bands, and the band gap reduces. Band width increases as you go to higher and higher energy levels, and the band gap reduces. Let's say, so for all energy levels will now become energy bands when you go to group of atoms instead of single atom. And the first observation from Bloch theorem or chronic penny model especially is this band width increases as you go to higher and higher energy levels. Bandwidth increases and band gap reduces as you go to higher and higher energy levels. So here this is the band gap. So that also can be verified, probably in the next semester in your solid state physics lab. Okay, so the simplest model, particle in a box, you can verify the validity of uncertainty principle. The ground state energy is because of the uncertainty, and energy levels are stationary. You can explain the concept of stationary states as well using this model, where length of the box is a multiple of n lambda by 2 for constructive interference. Length of the box must be some multiple of n lambda by 2. So then what is the quantization condition that you come across? If you use a similar kind of equation, here it is 2 pi r is equal to nh by 2 pi. 2 pi r is equal to n lambda. Here it is L is equal to n lambda by 2. So we'll see that. But here also you got a quantization condition. that only certain states exist, and those states are characterized by the wave function with n lambda by 2 fitted into the box, right? And energy level separation increases as you go to higher and higher energy levels. And continuation to that, when you go to group of atoms, when you go to chronic penny model using the similar setup, you'll get energy bands instead of energy levels, and band width increases as you go to higher and higher energy levels, and band gap reduces as you go to higher and higher energy levels. They can be verified. So as of now, in this model, within this model, ground state energy is non-zero, which arises through uncertainty, and energy levels are fixed by quantization condition given by n pi by L, and then energy gap increases as you go to higher and higher energy levels. Right, so with that I am closing this session.